Hi, my name is Andrew McLaren, and I want to help you with the resistor and capacitor laws for when you have them in series or in parallel. And most students feel pretty comfortable with doing these calculations, but then struggle when you're doing the ones where it's like the inverse, where you've got like CT in the bottom, and then C1 in the bottom, and C2 in the bottom. And what I want to do is help you get a big picture perspective on this so that you can at least identify the ones where it's just easy to add them up, like the series for resistors, where you're just adding up the two resistance, and the capacitor when you're adding up the two capacitor values. If you can understand those, then you know that the other case is the inverse. But the big picture on this is that the reason we're able to add these up here when we've got this series of resistors is that they have a common denominator. Like the denominator is the same for them, and they've just got different numerators. And same for when you've got this capacitor here. These two capacitors have a common denominator, and their numerators are going to be slightly different, but you can just add up those numerators, and that gives you like the total numerator for the CT. So that's the big picture, is trying to think about like what is in the numerator and denominator, and is it a common value in the denominator? If it is, then it's pretty easy to add them up. Otherwise, you have to then do an inverse to make their common numerators now the common denominators. So I'll talk about that a little bit more and kind of show some calculations and point to some of those like derivations of those formulas. But that's the main idea. And it's either going to be either the voltage or the charge or like the flow of charge, aka that amp value, that's going to be split. So if you understand those concepts, then it's going to be one or the other. And is it the numerator or the denominator that's being split for this formula? And that should help us out with these calculations. So we're going to look at all four of these drawn models, one where we've got a capacitor that is in parallel, and then another one with capacitors there in a series. And then we're going to look at vice versa, the resistors when they're in a series and resistors when they are parallel, and kind of talk about those formulas and how those are related and slightly similar and slightly different. So let's zoom in a little bit to this first one here, this one in red. This is a capacitor, and if you know your formula for capacitor, that's going to be this C is equal to Q over V. That's the generic formula for a capacitor. And so if we have the big total capacitor, which is these two put together, that is going to be the total charge over the total voltage. And if you see here, we've got actually, in this case, when you have a voltage, there's like a big voltage. This is going to be like the battery's difference between the two sides. So you can think of that as VT. And then change in V1 and change in V2, that is VT. So like VT is V1, is V2. So that is kind of like the common denominator. So when you have a common denominator, instead of writing out C1 as Q1 over V1, you can say this is Q1 over VT, right? And then you can basically say that C is going to be Q2 over VT. And so you can say that the basically C1 plus C2 is going to give you CT. Because they have this common denominator, you can think of kind of like adding up those different parts together. And this is the same as what I've written in there. I've just added in a little substitution with the Q1 and Q2 up top. So I know that these two charges are being split a little bit differently because some of the charges are going to go onto this capacitor and some of the charges will go onto the other capacitor. So it's a little bit of a split between the two. If one is a better capacitor, if it can hold more charge at the same voltage, it will take more of those charges. So we could calculate the exact charges on these two capacitors if we wanted to, if we had a voltage and their two capacities that they could give or have. Now it's a little bit more complicated here when we've got the inverse. For your brain, it's a little bit harder to see, but we've got the same formula here where C is equal to Q over V, but now the voltages are what's being split. So the denominator in this formula is what's being split. So if you were to look at C1 and C2, they've got different denominators in there. So you can't just add those two up. So if we're looking here, the voltages are going to be a little bit different. I did make up some numbers here to say like, okay, let's say that we have, I think like 1 voltage going all the way around, and we had two capacitors that were equally good and they were each going to get half of the voltage. Because like if you have two capacitors that have the same capacitance, then it gets kind of split evenly between the two there. But the big picture on this is that you want to think about how the charge is going to be the same on both these capacitors when they're in series. And you can really think about that in this middle piece here, where it's like, well, these minus charges, they didn't come from these plus charges. They came from within this section of the wire. And so as much as this is negative, this should be positive. So it's the same Q that's being split. So you kind of have like the same numerator if you were to try and line them up regularly here. So they've got like the same numerator and different denominators, which is kind of a problem for us math-wise. So instead of doing CT, we do 1 over CT. So you kind of flip the numerator and the denominator, and now you've got the voltage in the top, which is pretty easy mathematically because that's being split and you have a common denominator now that you've got the inverse. So you can then rewrite these as like 1 over C1. So this is going to be 1 over C1 and 1 over C2, those two different components, and they're just kind of like the inverse. So if you've got the numerator being split, then that's good. But if the denominator is being split, then you have to do the inverse to get that to being the numerator that's being split. So then if we're talking about resistors, you can have two resistors in series. They should have the same current flowing through them because they're part of one loop. And now there's a slightly different voltage, like jump down as they go through those two different voltages. So I like to think of this as like a waterfall height, and then there's like two different drops, or like water is being pumped up, and then it goes down a little bit, and then it goes down a little bit more, but it's still the same amount of water. So it's got that same amount of flow. So if we think about here, if you've got two resistors in series, then you can think of that as this V over I. That's kind of derived from V equals I over R. So if you get R by itself, it's V over I. So in this case, the I is still the same thing. And now there's two voltages that are being split. So you can split up the VT into V1 and V2 and work with that to say that the resistance formula here is just the first resistance plus the second resistance. So they're going to help there be more resistance in general. They kind of like add up. And then here I just did like a little basic math thing. If you're like, wait, what's going on with this common denominator? Why can't I add up things with different denominators? I'm kind of confused. You can kind of add them up, but you have to multiply to get them to have a common denominator. So if you remember from like middle school, like these two, yes, you can add that up. That's pretty easy. These two, you cannot add up as is. So you need to make them have common denominators if you want to add them up, which is doable with these problems, but it's typically not the fastest way to get the answer. So here we've got two resistors that are now parallel to each other. And in this drawing, you can see that there's a slightly different flow going down one versus the other. So maybe this is like two parallel waterfalls and they're both getting a little bit of water, but one might be getting more than the other. But we can see that we have this change in VT right here, which is the same as change in V2, as well as change in V1. Like they are the same value. So now we have the same voltage across all of these. So that's like we want to have be the denominator. To make voltage be the denominator, we have to do the inverse of R1, and then you can get voltage down in the bottom. And then you can kind of split up the two charges and rewrite that out as the 1 over R1 and 1 over R2. So that is how I like to think of how these things all relate. So let's look at some simple numbers to see how these calculations work. So if we're looking at a two capacitor system when they are parallel, you can see that the Q will be charged and we've got the same voltage. So if we know that the total voltage is going to be 10 volts right here, that means that both V1 and V2 also will be 10 volts. And we can use our capacitor formula here to see that this generally capacitors are going to be Q over V. So if we're thinking about the CT thing, this is going to be the same denominator here. So we're just adding up two different charges that are being distributed a little bit more on one capacitor than the other, and we can actually solve those numbers knowing what we have here. So the capacitor total here should be equal to C1 plus C2. We have those two values, so we just kind of plug those in like so, and we can see our total capacitance should be just those two other numbers added up. And if we're thinking about CT in the context of the total charge and the total voltage here, we can say now that we've got 11 Faradays on this imaginary capacitor that is in place of this two-part system. So it's kind of like, let's just imagine there being one capacitor here instead of two. You can think of that as now being that large capacitor that has this total charge, and this is being done over 10 volts. So if you do a little bit of math here, you can see that the total charge should be, was that 110 coulombs? And we can even go back to our C1 and C2 values, and knowing that those are going to be like Q1 over V1, but it's really the same thing as VT here. We can say that we've got our first capacitor was 1 Faraday, and that was going to be over 10 volts. And so the Q1 value ends up being 10 coulombs there. And then we can do the same thing for C2. But now you've got a second charge, and it's all over the same voltage, but we can call it V2 in this context here. So we've got the C2, which I believe we said was 10 Faradays, and that is over 10 volts. And so this Q2 value ends up being, what is that, 100 coulombs? And you can see that Q1 and Q2 do add up to the total. We can see that we've got, I think it was 10 coulombs plus 100 coulombs is equal to 110 coulombs. So that's one way of doing the math, just to kind of see how this works with the two capacitors that are parallel. It is unfortunately a little bit more messy when we're doing the inverse formula, but it is doable. So let's look at the same sort of thing. We've got this voltage difference of 10 volts, and let's say that capacitor 1 is 1 Faraday, capacitor 2 is 10 Faradays. And let's just kind of think through this problem. It's going to be very similar, but a little bit different. So the formula that we're going to need to use here is going to be the inverse, but you can kind of see that when we look at C is equal to Q over V. Now the V's are being split, so we want those in the numerator. And we're going to have the Q total just being like the same thing across these two different capacitors. So if we really want to have the same numerator or same denominator, we're going to need to do 1 over CT, because that ends up getting us VT over QT, and now we've got a denominator that really is constant. So if we do 1 over CT, we can then do 1 over C1 plus 1 over C2, and we have some values here. So we've got 1 over 1 Faraday plus 1 over 10 Faradays, and that should be equal to our CT value. Now, probably the easiest way to do this is a little bit of just using the decimals. So this is just like 1.0, and this is going to be 0.10, and that's going to be added up to the inverse of 1 over CT. So we can say this is 1.10, and I guess this is per coulomb, and then this is 1 over CT, because if we're thinking about the units, these are still per coulomb. And then if we want to get CT by itself, we take 1 and we divide that by 1.1. So the CT is now equal to 1 over the 1.10 per coulomb. And we can do a little calculator work to get that number. So if we just think 1 over 1.1, and you get 0.909 for this thing in terms, actually, yeah, this is going to be Faradays, not coulombs. That's my bad. Coulombs is charge. In any case, we have this new Faraday value for the CT, and you can then think back to what we were talking about here earlier with these numbers. and kind of plug that in. So we've got the 0.909 Faradays, which is the CT, and we do know what the voltage is that's total. This is going to be our 10 volts, and then we've got sorry, I think no, this is the 10 volts go down here because this is there, and I was just looking at the inverse formula here, and that was getting me a little bit thrown off. And we can look at the QT, and we can calculate that. So if we think about that, those numbers there, then that's 10 times this. So QT in this case is 9.09 coulombs. And we can then go back to the C1 and C2. So in this context of this problem, C1 is equal to the QT, which is the same as Q1. And this is going to be over the voltage total, or the, you can think of that as voltage 1 actually in this context here. Yeah, because it's not V total. So this is kind of like the QT, and it really is over V1. So we said that this one was 1 Faraday for its capacitance, and then Q is going to be that 9.09 coulombs, and then we've got V1. And V1 here, we can do a little bit of math there, is going to be, I think it's 9.09 volts for V1. And we can do the same thing for C2. And like it really is the same total charge here, but now we've got this V2, and we can plug in those numbers here. So if we think about this, we've got, I think it was 10 Faraday, and this was the 9.09 coulombs, the same charge across the two. And then we've got V2 here, which I think we're solving for. Yep, and then V2 here ends up being, what would that be? 0.909 volts. And if we added those two up, you can see that VT is equal to the V1 plus the V2. So we've got, what is that, 9.09 volts and 0.909 volts. If you add those up, it's going to be about 10 volts across the two. So this does work out. I added a few more sig figs just to help these numbers come out a little bit closer, because if you round a little bit too early, it's going to affect your calculations. But that does work out, it looks like, with what we were talking about above. So let's kind of think about these guys, and it's going to look very similar mathematically as what we just did above, but we can then do this with the resistance. So we've got that resistance formula here, where now resistance is equal to, it's just a rearrangement of VIR. So resistance is equal to the V over the I. And so if we look here, we've got the same I going across the two when they're in series here. So this is the relatively easy one. We're starting off with the easier calculation. So RT is equal to the VT over the IT, and IT is constant. So you can just say that this is V1 plus V2 over IT. And so long story short, the RT is equal to R1 plus R2. So it's not too bad. So if we throw in some numbers that say that we've got the VT is equal to 10 volts, and let's say that R1 is equal to 1, no, that's not the unit. What's the unit of R? Amperes for current, and no, I think it is ohms for resistance, yeah. And then R2 is, let's do 10 ohms right there. So R2 is a slightly better resistance, so you should expect a bigger voltage jump there appropriately. So if we're thinking about the RT, then it's just a matter of adding up those two numbers. And we've got 11 for our total resistance here. And then RT is equal to the VT over IT. And we have RT now, we just solved for that, and we had VT. So let's say that this is 11 ohms, which is equal to 10 volts over IT. You can isolate for IT there. I believe that's going to be 10 over 11. So these numbers are going to look very similar. So that would be that current that we're seeing there, and that's going to be amperes right there. And we can then plug in our specific things for R1 and R2. So we can say like, okay, I've got R1, which is equal to its velocity difference over 1 and its charge that's going through 1. Luckily, it's the same value as what we had here for the IT, because the IT is going through both the first and the second resistance. So you can think of that as the same IT. And we've got now V1. So we have this and we have that, so we should be able to solve for that. So I believe the first resistance, yeah, it was 1 ohm. And the IT is now this 0.909 amperes. And then we've got that V1. So I think V1 now is the 0.909 volts. And we can do the same sort of thing for R2. It's going to be equal to the I2, which is the same thing as IT. And then we've got the V2 jump going on between those two. You can kind of see what it's going to be. It should be like 909, I believe. But we have now resistance 2, which is 10 ohms. And the current, which was 0.909 A. And then you've got V2. Yeah, if we look at this V2, I think looks like it should be 9.09 volts there. So that works out really nicely. And you can imagine that we can do this also for this last one here, but we have to be careful because we're going to have the inverse. So we've got the same sort of stuff here, but now it's the relationship is going to be the 1 over RT is equal to 1 over R1 plus the 1 over R2. And so if we want to figure out its new resistance, we have to plug in these numbers. And let's say we're doing the same thing. We've got the 10 volts total. Let's say R1 is going to be 1 ohm and R2 will be 10 ohms. And we got to combine them to get this new RT. So we've got 1 over the 1 ohm plus 1 over the 10 ohms, and that should be equal to 1 over the RT if we plug those in. So we can then work with the decimals. Those are a little bit easier. So we've got 1.00 over an ohm added to 0.1 over an ohm. So we end up getting 1.10 per ohm, and this is 1 over RT. So if we want to solve for RT here, it ends up being that 1 divided by 1.1, and you're probably like, okay, I kind of get it now. 909. Now is this resistance here. And we can then go back into the larger thing. So we've got the resistance total, which is going to be, what do we say? V over I total. So now that we've got that resistance total, we've got the 0.909 ohms is now equal to the total voltage, I think we said was 10 volts, and the IT. So then you can plug that in, and the IT, we got 10 divided by 0.909. It's about 11. I'm just going to round that to 11.00 for that amps. And we could then also look at the R1 and the R2 calculations, knowing that that is now going to be the voltage, same voltage is that V1, which is going to be equal to VT. And now we've got the I1, which is not equal to IT. It's going to be a part of it. So the I1 plus the I2 should be equal to IT. But we have that resistance, we have that voltage, so we should be able to solve for that current. So I believe that the first resistance we said was 1 ohm. The VT is going to be the 10 volts. And then you've got that I1 right there. And I believe we can just kind of look at that number and kind of see that. So it's going to be 10 amps right there. So we know this I1 should be 1, just kind of like from the numbers. But now we've got the V2 over I2, but that V2 is the same thing as VT. We've got that I2, and we can just kind of plug these in. So we have that, we should be able to solve for that. So we've got the 10 ohms, which is equal to 10 volts over I2. I2 is equal to, it looks like 1 amp. So if we then end up combining that, I1 plus I2, that equals to the I total. And you can see that we had 10 amps plus 1 amp is going to be equal to 11 amps. So that does match with what we said earlier here. All these numbers seem to be working out. So you can do the same thing, but instead of 1 in 10, you can do 1 in 100 and kind of see how that affects things. Broadly speaking, these things either kind of work together to make the number add up, or the final number is kind of like a little bit less than the two, but it's kind of like an average of the two, but it's not exactly an average, but gets close to one of the values, depending on how much the other value is kind of throwing it off. So if you do like 100 or 1,000, that's kind of an interesting thing to do these same calculations in and see how it changes the capacitance of the total system or the resistance of the total system. It's yeah, it's kind of complicated stuff. So I've already worked through these problems, but these are some problems that I've had from students that I was tutoring. This one was asking about the resistance and how you can write out the resistance formula. The current, the total current going through this. So they were asking about like, okay, now let's think about I and how that's related to the V and the R and how that all kind of relates here. And there was one option that worked here. I think it was A, and it's kind of weird, but you can see that this is, they're making a common denominator to get to that, to being able to add up these different resistances. C did not work, and we'll kind of talk about why that's the case. So if we're thinking about I, then that's going to be VT over RT, and you can rewrite that here and do a substitution. So we knew 1 over RT in this case is equal to 1 over R1 plus 1 over R2 plus 1 over R3. You cannot add those numbers unless you have them have a common denominator. So you can kind of see I've done the first term here, and that looks very similar to what they have right here with the R1, R2, all over that stuff. This is the R2 over R3, so that's like this middle term. But you're going to get the other two terms by making there be a common denominator. So that's basically how you want to think about this problem. There was some confusion thinking that C was correct, but this is actually VT times 1 over R1, not actually R1 plus R2 plus R3. So if you use the wrong relationship here, then you might kind of substitute things in incorrectly. And so you want to just be kind of careful about that. These problems are a little weird for your brain for sure. So there was another problem here. I'll just kind of snip it so you can actually see the original problem. There was a bunch of capacitors, and they wanted you to combine them to figure out how it all relates as a whole system. So the way that I think about this is that I can see that the charge is getting split here. So you've got this total current and this total current going through this whole system. So you want to do the total current relevant pieces last, and you want to do the things that are being split first and kind of figure out what those new capacitors are and then kind of work out from there. It's kind of like your order of operations. So if I look at here, you can't combine things until you've worked through this a little bit. And I created a game plan, and I was like, I know before I even did numbers, I know that I'm going to have to combine these two to make some sort of capacitor there. And then I'm going to need to combine these two to make some sort of capacitor there. And then I need to combine those two new capacitors to get the final combination right here. So I kind of knew that was going to be the case, but the student I was working with was like, let's say that I've done this first step correct and I've gotten to here, but let's say I accidentally combine this green one with this other thing. Like, how do I know not to do that? And it really comes down to the fact that there's a different current flowing through this green part than through here because the current's getting split. So you can't add those two up unless they have the same current flowing through them. So if you remember what I was just talking about the current flowing through the same when you have two things in series, that would not be the case if you accidentally did these out of order. Because they have different currents, you can't really be working with them saying that there's that equality that allows you to combine them. So you need to be working on like these smaller loops and condensing them down into a single capacitor before you can do the larger system. And it has to do in large part with the current and how it's flowing through here. So you can kind of see I've labeled this as IT, I1, I think I2, and then I did I3 and I4. So I needed to combine those currents I3 and I4 to get my I1 and figure out what's going through that bigger capacitor with the I1, which would be appropriate with this capacitor. And then I2, I needed to combine these two things to figure out what's going on with that bigger capacitor there. And then that lets you kind of appropriately account for this stuff. So you just need to be careful, and it's kind of like order of operations. You gotta be doing things that are further inside before you go outside to the next layer. And it has to do with the qualities. So if things are not actually equal, you can't do these capacitor rules. Like what I was just saying, like don't do the green with this black part before you've combined it with the blue. Because those then need to have a better representation of the system. Yeah. Thank you for McLearning with me. Before you go, please check out the following services that I offer with my business. So if you click the link in my videos, this goes to my website. I might be changing it from Podia because I'm no longer doing the interactive videos for sale. I might put those up for free. But most of my other services are linked here. So you can see that I've got like a Teachers Pay Teachers and a Wyzant. The Teachers Pay Teachers has a lot of my assessments that I have for like the NGSS, as well as lessons that I made when I was actually a teacher in the classroom. So I've got quite a few things like CERs and other things on there. If you want to get one-on-one live support from me, either like with science or like working on like teaching support lessons and that kind of stuff, you can sign up through Wyzant. I have a link to there where you can contact me there, and we can schedule hourly appointments. And I've got a few other things on here like a Facebook page and other social media. And if you're interested in getting professional development with me for like a team of teachers, a whole page with information on that. So yeah, feel free to check that out. Thank you.